Hey everyone, and welcome to The Explainer. Today, we are taking a really fun look at the hidden math of how we measure our physical reality. I mean, we're covering everything from estimating the massive weight of a fully grown elephant all the way down to calculating the exact volume of a single teardrop. So, let's jump right in. Here is our roadmap for today. We're splitting this explainer into two distinct tracks. First, the solid world of weight, covering our intuition, grams and kilograms, and a real-world test. Then we pivot to the liquid world to measure capacity, looking at liters, tiny milliliters, and finally, the real cost of a leak.
All right, part one, the intuition of weight.
Okay, let's dive right into this. Picture a lineup. You've got an ant, a squirrel, a dog, a giraffe, and an elephant. Relying purely on your everyday intuition, just mentally order them from heaviest to lightest. You know, you don't need a textbook to tell you the elephant comes first and the ant comes dead last, right? You actually already understand the core concept of weight completely naturally.
And estimating weight like this starts in super common everyday scenarios. Imagine you're at the local vegetable market, watching the seller use one of those traditional balance scales. When you look at half a pumpkin sitting there, what do you think it weighs? Is it less than a kilogram? More? We literally make these snap estimations all the time, constantly testing our gut intuition against the real world.
Moving on to part two, mastering grams and kilograms, the standardized rules of weight.
So here is our absolute anchor, the golden rule of this whole system. 1,000 grams equals exactly 1 kilogram. Every single calculation regarding weight from this point forward is just a mathematical manipulation of this one fundamental rule.
And this brilliantly illustrates exactly how that math plays out. If you have a 1 kilogram bag of dal sitting on the left side of a balance scale, well, to achieve perfect balance on the right, you need exactly two 500-gram bags. Half a kilo plus half a kilo equals 1 full kilo. It just totally demystifies the fractional math.
Let's apply this to a delicious, practical math problem straight from our source. Meet Mr. Srinathan. He's a sweet shop owner who has all these orders for 1 kilogram of Kaju Katli, but his customers want them packed in entirely different sized boxes. So if Mr. Das wants 500-gram boxes, Mr. Srinathan needs 2 boxes. But Mrs. Fernandez, she wants 250-gram boxes, which means he needs 4 boxes to make that kilo. Mrs. Khan wants 100-gram boxes, so that's 10 boxes, and Mr. Patel wants these tiny 50-gram boxes, meaning it takes 20 of those little boxes to equal that same 1 kilogram of sweets. The total weight never changes, just the fractions. It's like a giant puzzle.
Which brings us to part 3, the real-world weight test, how all these numbers actually feel.
Think about the last time you grabbed something from the pantry. Typical 500-gram packets of sugar, poha, or dal fit super easily into just one hand. But contrast that physical experience with trying to heave a 10-kilogram bag of atta or, wow, a 50-kilogram sack of rice. The math on a page gives us the number, for sure, but our muscles are what reveal what those kilograms actually represent in the real world.
And hey, speaking of muscles, get a load of this incredible real-world fact from the text. Indian weightlifter Mirabai Chanu won the silver medal at the 2020 Tokyo Olympics. Now, she was competing in the 49-kilogram event, but she lifted a staggering total of 202 kilograms. Think about that for a second, relative to those 1-kilogram bags of dal we talked about. She lifted the equivalent of over 200 of those bags. It's just a phenomenal example of human strength relative to standard kilograms. Absolutely mind-blowing. Okay, let's switch gears for a second and create a mental bridge here. Up to this point, we've been dealing strictly with the solid metrics of weight, kilograms and grams. But how do we measure things that flow? You know, things that definitely won't sit nicely on a balance scale? For that, we need to shift our minds over to the liquid metrics of capacity, liters and milliliters.
Welcome to part 4,
Pour it, measuring capacity.
Now, what's really interesting about this is how visually similar capacity is to weight. Just as 1,000 grams make a kilo, 1,000 milliliters make a liter. If you've got a small 250 milliliter bottle, you have to pour it exactly 4 times to fill a 1-liter bottle. It's literally the exact same fractional logic we just used at the sweet shop, but with liquids.
Moving to part 5, liters, milliliters, and drops. Let's look at the really tiny stuff.
Think about your kitchen or your medicine cabinet. Cough syrup is usually measured out in little 5 or 10 milliliter dosing cups, right? A teaspoon of honey is just a few milliliters. Cooking oil might be poured in 50 milliliter increments. But the most fascinating everyday application has to be eye drops. As the chapter points out, when you use eye drops, you are using less than 1 milliliter at a time.
A single drop is merely a tiny fraction of a milliliter. That is some incredible microscopic precision happening right in your own home.
And just like we guessed the weight of that pumpkin earlier, we can totally practice estimating capacity too. Imagine trying to guess the volume of mugs, bowls, and buckets right there on your kitchen floor. Try estimating how many milliliters your favorite coffee mug holds, and then actually grab a measuring jug to verify it. Honestly, it's the best way to physically connect with the math.
Finally, part 6, the cost of a leak, how those tiny drops add up.
Consider just how much water we consume every single day. I mean, the scale is massive. A thirsty crow might drink just a few milliliters at a time, sure, but an elephant drinks an enormous volume of water every single day. And us humans? We use water for taking showers, watering crops, washing clothes, often blowing through hundreds of liters a day. When you truly understand what a liter actually represents, you really begin to grasp the sheer volume of resources we rely on to live.
Which brings us to one final, kind of provocative thought to leave you with. If you place a container under a leaking tap for an hour, how much water gathers from just a slow, continuous drip? Now multiply that by 24 hours. A tiny fraction of a milliliter, dripping repeatedly, suddenly balloons into wasted liters. Understanding capacity is ultimately crucial for protecting our real-world resources. So how would the water wasted from a single drip affect us all over time? Something to think about. Thanks so much for joining me on The Explainer. And hey, keep exploring the math all around you. See you next time.